So in this video, I want to talk a little bit about dense subsets of the real numbers. So first of all, we say that a subset G of the real numbers is dense if for any real numbers x and y with x less than y, so there exists an element G in the set G such that G is properly between x and y. Okay, so this intuitively means that if you pick any two real numbers, you can find an element of G that's between those two real numbers. Okay. So, theorem. If we have a set G, there's basically two equivalent definitions of density. So the first is the one that we gave up here, and then the second is that for any open subset of the real numbers, there's an element of G contained in that open set. Okay, so these are equivalent definitions. Just to illustrate with a quick example, the easiest example of a dense set probably is Q. So Q is dense. And you can kind of see this two ways, right? One is that if you have any open set, it definitely contains a rational number. So like interval from 0 to 1, that definitely contains a rational number. The endpoints could also not be rational numbers, so like square root of 2 pi, for example. So that's an example of an open interval with irrational endpoints, but it definitely contains rational numbers, right? And you can see that, this definition up here holds for the rational numbers, because, like, for example, if you have any two rational numbers, like these ones, for example, you can always find a rational number that's between those two rational numbers. So in this case, an example would be like 5/8. Okay, and you can show that this is true for irrational numbers as well, that there's always a rational number in between any two irrational numbers. But okay, so I want to prove this theorem here. And so we're going to start by proving the forward direction. Okay, so the forward direction is we assume that G is dense. And that's, again, using this definition up here. Okay, and then we want to let O be any open set. Okay, so and then our goal is to find an element of G that is contained in O. So the first thing I want to do here is I want to consider some elements of O. So let's erase some of this here. So we want to let X be any element of O. And we want to recall that because O is open, right? So the definition of an open set is that for any element of the open set, there exists an epsilon such that, or with the property that, X minus epsilon, X plus epsilon is a proper subset of O, or is a subset of O. So this is also known as the epsilon neighborhood around X. Okay, but another way to think about this is that we have this number X minus epsilon, we have X plus epsilon, and then we have X, right? So then X is less than X plus epsilon. And then if we go back to our definition of density up here, right? So we can always find an element of G that's between any two real numbers, right? And so in this case, these are kind of our two real numbers. So there exists G such that, or there exists G, which is an element of G, I should say, such that X is less than G is less than X plus epsilon. Okay, and then this proves that G is an element of O, right? Because then G is in this neighborhood right here, and this neighborhood is a subset of O, right? So therefore, then G is an element of O. Okay, so that proves the forward direction. Okay, so then the only thing that's left for us to do is to prove the reverse direction. So for this direction, we want to assume this part up here, right? So we want to assume that for any O subset of R with O open, G is an element of O for some G and G. Okay. And now what we want to do, so now let X and Y be any two real numbers. So, and assume X is less than Y, it doesn't really matter. And then what we want to do is we want to consider the interval, right? Because there's an interval whose endpoints, an interval that starts at X and ends at Y, which is an open interval. So which is open. But then because this is open, by assumption, there's an element G that's an element of this open interval right here, right? So then there exists G and G with G contained in this interval. But then G is contained in an open interval from X to Y. So that proves that, that X is less than G is less than Y. Okay, and then that proves that, that G is a dense set. So that concludes our proof, and thank you very much for watching.